Okay, here we are with our third section of the trilogy of logic. This is logic implementation. So now if we are given an equation, we can sketch the circuit, and of course to test that the circuit is right, we also need to know how to get the truth table, which we did in the past sections. All right, so the other thing we're going to look at with this is also a little bit of optimization. Okay, we have two different types of circuits we can do. We can do an AOI circuit that is sum of products. And we can also do product of sums. So here, and that is very hard to see for you guys, isn't it? Yeah. The lines are really hard to see. I'm not sure why. Let's see, is this working? So what we have, but basically where we're at, once we have an equation, can we sketch the circuit? Okay, the first example is already drawn out for us, but there's some problems with this. So if we look at this, what do we have? We have A naught B, C naught D. So that's all going together here into a 4-input AND gate. And then B, C, D naught, all of those terms are coming into a 3-input AND gate. And then A, B naught is coming into a 2-input AND gate. And then we have also a 3-input OR gate that's ORing them all together. The problem with that is it's going to come down to optimization, and also the fact, Carson, that there is no 3-input OR gate. It doesn't exist on a TTL chip. Okay, so what do you have to do? You got to cascade them together. And even if it did exist, let's see. Let's do a little bit of how many parts would we need for this? So we start counting ICs and gates. So in terms of the gates, let's see. We would have actually I kind of wrote that backwards. Gates, ICs. Okay, we have 4 inverter gates, right? But all 4 of those can be wired on one chip. Okay, we have a 4-input AND, so that would be a separate chip. We have a 3-input AND. And we have one of those. We only have one of each of those, but that's going to be on a separate chip. And then we have a 2-input AND. And we only have one of those. And so that's going to take a separate IC. And then we have one 3-input OR. Already talked about the fact, even though that doesn't even exist, in total, that is 1, 2, 3, 4, 5. In total, we would need 5 circuits, 5 integrated circuits, 5 chips to wire this circuit. Okay? So what we typically do is we want to also optimize it. I think it is on. What we do want to do is optimize it. And why is it not easy? There it goes. Okay, and only use 2-input gates. Okay, so we'll sketch that out with 2-input gates. So if you notice, sometimes you'll see gates drawn horizontally. What we usually do, it makes it better, is if you have your 4 variables or 3 variables, if you line them up vertically, and then each one of those can go, and we do need an inverter for each one of these. So if you sketch your inverters coming in vertically, and then to build your circuit, you can then have your ands and ors going horizontally. And it takes a little bit of planning so you don't end up with a bird's nest. What do I need? I need A naught ANDed with B, C naught, and D. So the best way to do that would be to come down. I'm going to just come down. I'm going to be ANDing A naught with B. So we'll come down and we'll AND those together. Right? So what do I have here is A naught B. And then I need to AND that with C naught D. I'll come down here and AND those together. And it would be better to bring those two together rather than bring three pieces. You know, it'd be better to do that rather than A naught B and C naught. It just, because of timing, it works out better if you have four terms to AND two at a time and then AND those two together. So then if I AND those two outputs together, that gives me A naught B, C naught D. Right? And then what's other terms do I need here? I also need B, C, D naught. And we lost our circuit because I tripped the sensor. Come on back. I'm going to have to go back to the back. Isn't this fun? All I got to do is touch the mouse and it comes back. Okay, so then what do I need? I need B and C and D naught. So since we have crossing wires, that's where we always want to make sure we are sketching nodes. Okay, to show that that's a junction. So I've got a junction here. So now I have, oops, I drew that wrong, didn't I? That would have been BC naught. I need BC. Okay, so anytime we have crossing wires, if there's no, you draw nice straight lines, no node for a junction, then there's no node for a junction, then they're just crossing wires. They're skipping over top of each other. Okay, so that is what? That is BC. And then I need to AND that with D naught. So I'll bring those together. So now I have BC D naught. And my last gate that I need is AB naught. So there's A. There's B naught. Okay, and then what do we have to do with all those? We got to OR all of those together. So that means we're going to have to OR two together at a time. And bring the rest together. So final circuit would look something like that. And of course, that's going to have to go to a probe or something so we can figure out if it works. Okay, so this is just, again, this is the third piece of what we're doing. We had truth tables and logic expressions, and then we had our logic analysis where we have the circuit. Now, given the circuit, sketch out given the equation, sketch out the circuit. Okay, well, the other thing that we looked at with the other one is, what about the number of gates and ICs needed in this circuit compared to the other one? Well, inverter gates, what do we have? We have inverters, we have AND gates, we have OR gates. Okay, so how many inverters do we have? We have what, 4? 4 inverters. We have 6 AND gates, and we have 2 OR gates. So even though this has more gates, it's going to have fewer chips. Okay, this is going to be 1 IC, and there's 4 2-input gates on 1 chip. That's why it's called a quad input, or a 2-input and quad, because there's 4 on there. So that's going to take 2 chips, and it's only going to take 1 chip. So in total, this circuit is more efficient. This will only use 4 ICs. Also, the 2-input chips tend to be cheaper. So if you're really looking at what's the cost analysis, then that would go to another level, because the 2-input gates tend to be about 50 to 60 cents. The 3-input, 4-input gates, they tend to be in the 75 to 80 cent range. Now, we're not talking a huge amount of money, but if you're making millions of something, then it all adds up. Okay? Questions on that? Yes? Well, because there's only 4. Let's go back. Do we need to go back and look at what we did in Unit 1? Let's put a page in. What does the pinout for an AND gate look like? I can't put a page in until I use my mouse.
Oh, wait.
Okay. So what does the pinout for an AND gate look like? And then this is going to be important to breadboarding as well. You know, when we're looking at this, I could draw it just as fast as find a picture of it. But what does our chip look like? Chip looks like this, right? Okay, and we got pin 1, 2, 3, 4, 5, 6, 7. And this is a 74 LS08. So what happens with this chip? Pin 1 and 2 go in to an AND gate and come out 3. Pin 4 and 5 go into an AND gate, comes out 6. Pin 7, ooh, what does pin 7 have to be? Ground. And then on the other side, we keep counting around the chip. What do we got? We've got, this would be pin 8, 9, 10, 11, 12, 13, 14. What does pin 14 get? Power. So pin 14 gets power, VCC, and it doesn't go in. It goes, the inputs go in 9 and 10 and go out 8. So the gates are actually oriented in the same direction. Inputs go in, 12 and 13 goes into the AND gate, comes out 11. Okay? So, can I advance? Maybe. Okay, that was a sum of products. A product of some circuit is usually a little bit less common, but sometimes they are more efficient. It just depends on the circuit. So a product of sums basically does the same thing. What do we have? We have our OR gates first, and then they go into an AND gate last. So just we're switching our ANDs and ORs. Of course, in algebra class, what could you do? You could distribute all those out and simplify it, and that's something coming after Thanksgiving, even after sumo bot tournament at this point, That is called Boolean algebra, and then we'll learn how to simplify all that and get not only just a different, sum of products is easier to work with, but will also give us a simplified circle. Huh? Oh, you're saying no thank you, but yes, you were going to do it. Okay? That would be a lot of terms to simplify. But things cancel out too. But that's after sumo tournament at this point. So, again, talking about the same thing. If we have all these 4 input, 3 input, 2 input ORs going into a 3 input AND, what do we have? We're again going to have 5 ICs, right? Most of the time we want to build things and more efficiently, but also, I don't know why I won't go forward. There it goes. So, not only just more efficiently, but to only use 2 input gates. So, looks like, again, I need all 4, don't I? Do they all 4 need inverters? I have an X, a Y naught, a W naught, and a Z naught. I need all 4. So, if I draw this out, there's my W, X, Y, Z. And usually it's easier to manage if you do the longer ones at the bottom, just in terms of combining things. I've got W or X naught, so now I have to make sure I sketch an OR gate here. And then I need Y naught or Z. So we can go ahead and bring down Y naught or Z, or them together. So there's my first term, and then what else do I need? I need W naught or X, and then I'm going to OR that with Y naught. So there I'm going to need a node. And then I need W. So I'm going to need a node for my W or Z naught. Okay? And then, of course, we need to AND them together. Make sure you're making a distinction between AND gates and OR gates. AND gates look kind of like a D shape. They're round on the front. They have a flat backside. OR gates are concave on the backside, and they come to a point on the front side. Okay? If you just draw a symbol, you're going to really confuse me if you draw this. What's that? It's a carrot, or maybe a bird beak, I don't know. Okay, so just be very careful when you're drawing things out, because we need to make a distinction. And no, I don't like my new smart board very much. I'll use that excuse for the sloppiness of my AND gates and OR gates, as opposed to drawing it out on pencil and paper. But make sure we're making a distinction in our inverter gates. Of course, they got that little circle. And remember, we have other gates that are similar. What's that one? NOR, not OR. And not NAND. So don't put circles on the ones that have circles. on an AND gate or an OR gate because they don't have circles on the ends. The inverter does, but not the others. Okay? Are we more efficient here? Probably. Because how many, what do we have? It's the same as the other one. We're going to have four. We're going to have 4 different ICs. Okay? Questions at this point? So this is a pretty big section. If you look online on Google Classroom, you will see that I've broken this into a lot of little steps as well. Let's see, is this the updated one? Oh yeah, I think it is. Okay, so first of all, the first piece of this is drawing everything out and figuring out the truth table on pencil and paper. So we have basically 2 circuits that you are going to sketch it out. The original version of the curriculum has you sketch it with any number of gates, which I think is stupid because we have to build it with only 2 input gates anyways. So we got to draw it out, figure out your truth table from the equation, same as we did in the last section. And then we have a product of sum circuit. Product of sum circuit, the truth table, you'll have to do test points for to figure that one out. That one's not going to be as simple, right? The interesting thing is, those 2 truth tables should be the same. They are logically equivalent. So you got to do test points, but you have a built-in check. They should be the same. And then what you're going to do, you're going to model them on multisim. So that's going to be a separate grade. And after modeling, oh, that might be here, 5 and 6. After modeling them on multisim, then there'll be 2 additional separate grades for each of the breadboarded circuits. So we're going all the way through from design through prototype. And when we get to that point, there'll be some other things we have to do when we look at the multisim. Other things we'll have to look at to demonstrate, because I think you're probably going to need some help getting started with your circuits anyways. Okay? So get started on sketching circuits, figuring out truth tables, and we'll go from there. Oh, this is like a assignment that'll take some of you through Thanksgiving and beyond. Some of you may have homework on Thanksgiving if you don't have your breadboard working. If you wire it right the first time,